So if we still have time, then we can actually discuss on the semi-infinite. Okay. Yeah, for the exam, as I said, till whatever we actually discussed in the class, including the semi-infinite. Okay. So coming to the tutorial problems, first one says first three are actually from fins only. So you can actually go through any textbooks, heat transfer textbook. There will be actually lot of questions. So very good questions are actually there. Yeah, you have to actually go through many of the questions. Then only you will be actually able to understand, or you will be actually able to solve the problems. So here it is given two long copper ends of a diameter d is equal to 10 mm are soldered together end to end. So long copper. Okay, they are actually soldered end to end with the solder having a melting point of 670 degrees Celsius. The rods are in the air at 25 degrees Celsius with a convective coefficient of 10 watt per meter square Kelvin. What is actually the minimum power input needed at the junction to affect the solder? Okay, so that means two copper rods are actually being soldered. So it is actually given us long. Okay, so that actually gives us a hint that whatever we are actually dealing with is actually very long. So the length doesn't actually matter. It is actually very long. So and it is actually asked that the soldering is actually being done. It is in the convection. So that actually hints us that this is actually probably a fin problem. Okay, so we can see that a fin problem, it doesn't necessarily mean all the time the fin as it is. Okay, so there can be actually other practical purpose also for this particular equation. Doesn't always mean the actual fins need to be there and all. So there are actually practical situations where fin equations can be actually used, which is not actual sense it is actually the fins. So here what it is actually asked is what is actually the power input for the soldering such that uh, the base temperature need to be at 650 degrees Celsius. Okay, so two long wires are actually going to be soldered at the center. Okay, so if you see the picture, we can see that this is actually the long wire, and we can see that at the center we are actually going to solder it. Okay, so instead of fin, usually fin what we discuss is at the base it is actually having the maximum temperature and the temperature actually varying like this. Okay, but here you can actually see that this is actually happening at the center. Okay, so therefore first what we can actually what the meaning is that so yeah, so we need to actually the condition is that we need to actually have 650 degree at the center. Okay, 650 degree at the center, so that welding can be actually done. So that is actually going to be our criteria. Okay, so in yeah, and again it is actually said that the long, it is actually very long. So therefore what does that actually hint? It is actually a very long fin. Okay, so this can be actually take as infinitely long fin because it is actually given as a long fin. That's it, a long rod. That's it. Okay, so we got that it is actually a long, infinitely long fin. Okay, and also we got that TB, base temperature, should be equal to 650 degrees Celsius. Okay, yeah. So now, so now it is actually asked what is actually the minimum power we have to actually give it over here such that the welding can be actually done. That means the base temperature will be actually kept at 650 degrees Celsius. Or base temperature not, the center temperature will be actually kept at 650 degrees Celsius. Okay, yeah. So now what we are actually going to do is, in order to make it as a fin, what we have to actually consider is only the one portion. Okay, so we can actually consider only the one portion for that. Okay, so we said that, so now we can actually consider this as a fin with the base temperature at 650 degrees Celsius, and it is actually infinitely long fin. Okay, and it is actually having the heat transfer coefficient as well as at h as well as T infinity, etc. are actually given. Okay, and it is actually asked what is actually the minimum power we need to give. So that means what is actually the total heat that is actually escaped from here. Okay, so whatever the power we are actually giving to here, it will be actually convected out. So what we are actually talking about is actually the steady state condition only, right? So since unsteadiness, nothing is actually asked, so this will be actually steady state condition. So whatever the power we are actually giving at the center region for the soldering, so that is actually the power that is actually being convected out. Okay, so that actually makes everything actually simple. So, but because we actually know what is actually the total power transmitted for an infinitely long fin, it is equal to Q is equal to root of HPKAC, right? Yeah. So that is equal to root of HPKAC. Uh, I'm sorry. Yeah. So we know that Q total heat transfer from an infinitely long fin is actually Q is equal to root of HPKAC. So yeah, and what we are actually talking about is actually the from the center. It is actually happening on both sides, right? We are having now kind fin, a infinity long fin on both sides because we are actually soldering at the center. So the Q minimum Q that we need to actually give is 2 times root of HPKAC. Okay. So do we know HPK and C? We can check the question. Um, yeah. So a diameter we actually know. So from there we will actually get the perimeter as well as the cross sectional area. H we actually know. HPKAC conductivity of the rod is actually not known. Yeah, this is actually the conductivity. So this is actually the convective heat transfer coefficient. So conductivity, uh, yeah. So conductivity is actually not known, that we can actually assume some values, I think. Okay. So HP K AC. Yeah. So yeah, material is actually given as copper, right? Yeah. So material is actually given as copper. For copper, we can actually take the conductivity somewhere around 400 watt per meter Kelvin. Okay, so conductivity, if it is not given, but material is actually given, so that actually gives us the conductivity. We can directly, you can actually search in net or in some textbooks, and then you will actually get it. Okay, so that's why it is, yeah, here it is given as 379. If nothing is actually given to you, and it is actually said that conductive, the copper is actually the material, you can consider it as 400 watt per meter Kelvin, no issues. Okay, so from here you can actually calculate what is actually the minimum power given. Okay, so the catch is that you must actually realize that the soldering is actually being done at the center, and we are actually talking about fin on both sides. Okay, yeah. So that is actually how you can actually tackle this problem. Is that okay? Is that clear?
Yes, sir.
Yeah. So now we are considering the second one. So considering two long slender rods of same diameter but different materials. So here also you can see two long. So whenever it is actually said as long, you have to actually consider that it is actually infinite length. Okay. Until or otherwise it is actually given. So even if it is actually said that too long and all, and maybe somewhere it might be actually given as n can be actually considered as adiabatic. In that case, you have to definitely go with the adiabatic type. If nothing is actually given and simply long is actually what mentioned, then you can actually go with the infinite long assumption. So one end of the each rod is attached to a base surface material of 1000 degrees Celsius, while the surface of the rods are exposed to an ambient at 20 degrees Celsius. Okay, so two rods at the same base temperature and same condition, but different materials. By transversing the length of each rod with a thermocouple, it was observed that the temperature of the rods were equal at a position xa is equal to 0.15 meter and xp is equal to 0.75 meter. Okay, where x is actually measured from the base surface. So if you are actually moving along the length, so the same temperature we are actually getting for material A at 15 mm, okay, a 0.15 meter, and maybe just say take say 700 degrees Celsius. So if you are actually moving along the length for material A, we are actually measuring the 700 degrees Celsius at a 0.15 meter, whereas for the B material, we are actually measuring at 0.075 meter itself. Okay. Yeah. So if the thermal conductivity of the rod A is actually known to be 700 watt per meter Kelvin, it is not watt per meter minus Kelvin. It is watt per meter Kelvin. Kelvin should be actually come over here. Okay. Determine the value of Kb for rod B. Okay. Yeah. Uh, so first of all, what do you actually think? The conductivity of material B will be higher or lower than material A? What do you actually think? I mean, thermal conductivity of material B is actually higher or lower than material A? Because here,
Sir,
yeah,
are the
which
two
one?
rods connected end to end, sir?
Which one?
We have two rods, right, sir, here? Two cylinder rods.
Yeah.
Are those two rods connected end to end or both are connected to
No,
the
no, no,
base?
no. Both are connected to the same base. Both are connected to the same base. Okay. So it is
The B will
independently.
have the more conductivity, sir.
Yeah. So we will see. That is actually a very good hunch. So we will see once we actually see the value, then we can actually see off. Okay. So this is actually the condition. So two long cylinders we can actually see. Two long cylinders, material A and the same base material or base surface of 100. It is not 1000. It is actually 100 degrees. Okay. And the question it is given as 1000, but it is actually 100 degrees Celsius. Okay. uh, yeah. So the assumptions are actually obviously 1D dimensional negligible heat transfer from top surface and uniform convection of airflow. Okay, so these are actually the assumptions what we have to actually make. Yeah. So when what we have actually written is at x is equal to 0.15, we are having some temperature T. Okay, and the same T we will be actually having for material B at 0.07. Okay. So now, yeah. So we now know what is actually the base temperature. Okay, theta B we actually know, and we know that it is actually a infinitely long cylinder, long fin. Okay. So therefore, we can actually we can actually see what is actually the thermal variation or the temperature variation for an infinite long fin. Okay. Yeah. So it is actually given as e raised to minus mx. I think in our uh, so in our lecture, it is actually we have actually talked in terms of uh, cos HML and sin HML. I think. Okay. Yeah. So anyway, you have to be actually be familiar with both the yeah, both the ways in which actually it is written. If you actually referring to different textbooks, so the values given will be actually different. So some textbooks it is actually given in terms of cos hyperbolic functions, okay, hyperbolic trigonometric functions, and in some textbook it is actually given in exponential terms. Okay, but we know that cos h mx is equal to e raised to minus mx plus e raised to mx by 2. Okay, whereas sin h mx is equal to e raised to minus mx minus e raised to mx by 2. Okay. Yeah. So with these identities, you can actually play around and you can actually convert a hyperbolic to the exponential functions. Okay. Why we are actually using these star? It is actually easy for us to solve some problems in terms of hyperbolic and some terms in terms of some problems in terms of exponential. Okay. Uh, yeah. So for an infinite fin, it is actually given as theta by theta b is equal to e raised to minus mx. So where m we know, m is actually square root of hp by kac. Okay, so that is actually the m. And theta b we actually know as theta b is equal to tb minus t infinity, and theta is equal to t minus t infinity. Okay. So in this case, we actually know that theta by theta b is actually same for material A and material B. Okay, or for example, we can actually say theta at x of A is equal to theta b into e raised to minus mxa. Okay, and theta xb is equal to theta b into e raised to minus mxb. Okay, but we know that at some x, okay, at some at x is xa is equal to uh, xa is equal to 0.15 meter and xb is equal to 0.075 meter. We know that theta xa is equal to theta xb, right? But that at these points, theta temperatures are actually going to be same for both condition. So we can actually equate theta b into, because theta b is actually same for both the condition. Theta theta b into e raised to minus ma xa is equal to theta b into e raised to minus mb xb. Okay, so we can actually cancel off theta, and we know yeah, so therefore we can actually write as ma xa is equal to mb xb. Okay, so in this the only unknown is actually going to be the conductivity of material b. Okay, h we actually know. Okay, and the perimeter etc are actually same. Okay, perimeter and the cross sectional area are actually same on for the both materials. So if you actually still write, so hp by ka pro ka, oh, what is that? Hp by ka into uh, a cross sectional area of a and square root 1 by 2 into xa is equal to hp by kb into cross sectional area of b raised to 1 by 2 into xb. Okay, we know that cross sectional area, perimeter, edge, everything is actually same for both the materials. Okay, so we can, we know what is actually xa, we know what is actually xb, and also we know what is actually ka. So the only unknown is actually going to be kb. Okay, so from there you can actually calculate what is actually the conductivity of the material b. Okay, so is that clear?
Yes, sir.
Actually my other system is also going to be switched off now. Okay, so if I am not able to do this fully, maybe we can actually have a tomorrow session also. Okay, so I think my laptop will actually switch off now. uh, Power is actually still not there. So in that case we can actually have a discussion tomorrow and we can finish the uh, tutorial session. Okay. uh, yeah, so the third problem is finned passages. Finned passages are frequently formed between parallel plates to enhance convection heat transfer in compact heat exchanger cores. Okay. We can actually see the figure itself. So we can actually see that these are actually the fins, the vertical lines. So these are actually the fins. Okay. So we have to actually take heat from the top and bottom plate. So they are actually connected with the fins, and air is actually passed through these passages. Okay, so this is actually happening in many of the heat exchanger. For example, in your laptop also or in a CPU, you can actually see that we are actually having this kind of fins. Okay, so there is actually passages. You are having long fins, so the air will be actually passing across this one. Yeah. Important application is actually the electronic equipment where one or more air-cooled stacks are actually placed between uh, heat dissipating electronic components. Consider a single stack of rectangular fins of length L and thickness T with the convection conditions corresponding to H and T infinity. Okay, so this is what we are actually considering. We are actually considering only one, for example. Okay, so one channel we are actually considering. So what it is actually asked is obtain expression for the fin heat transfer rate QFO and QFL in terms of base temperature T0 and TL. Okay. So here the temperatures are actually TO on the top and TL on the bottom. Okay, TO on top and TL on bottom. So, so heat will be actually taken from both sides, right? So heat is actually being taken from both sides. Uh, where is this? I don't remember. Okay, anyway. Yeah, heat is actually being transmitted from top as well as bottom, right? So therefore, we can actually see that that's what it is actually asked. What is actually the heat transfer from the bottom to the fin, as well as whatever heat is actually transferred from top to the fin. Okay. So in the usual condition, whatever we actually saw till now, we were actually seeing about the fins with which is actually attached at the bottom. Okay. So usually we were actually seeing the fins which is actually attached at bottom. Okay. And we were actually seeing what the heat is actually being transmitted like this. But in this case, the fin is actually different. The fin is actually attached on both sides. Okay. Attached on both sides, and the sides, the temperatures are actually different, say T0 and TL over here. So heat is actually being transmitted from both sides. Okay. And it is actually getting out over here. Okay. So that is actually the condition we are talking about. So therefore, this is actually not a condition of whatever the conditions we usually see. Okay, so we have actually seen the free end, whatever the equations we derived till now, it is for free end with the conditions as prescribed temperature or the adiabatic condition or convective condition or infinite long like that. But this condition, it is actually doesn't fit in any of those cases. Okay, so therefore, we have to actually derive the condition over here. So we have to actually take a uh, new infinitesimal area over here, and we have to actually start from our basic energy balance. Okay, yeah. So that's what we are actually going to do it over here. Yeah. So this is actually our situation. From the top, QFO is actually coming. From bottom, QFL is actually coming. The dimensions and all those things are actually given. Okay. Uh, yeah. So here we have actually given us distribution is actually given, and we are actually writing theta is equal to theta t minus t infinity. Okay. So our basic governing equation is actually going to be same. Only the boundary conditions are actually going to be different, right? So basic governing equation we actually taken from the energy balance, right? So energy balance, heat is actually coming from both sides, and it is actually getting out over here. So for, used on the conditions, we are actually saying our energy balance. Okay, so the governing equations are actually going to be the same. So therefore, the solution is also going to be the same. Okay, so only that solution means the general solution. So only that these constants are actually going to be depend upon whatever our boundary conditions. Okay. Yeah. So here we can actually see that C1 e raised to mx and C2 e raised to minus mx. So here also you can see it is actually written in terms of exponential. Okay. The boundary conditions are at x is equal to 0. Okay. So it is not T0, it is not TO, it is actually T0. So length is actually starting from the top at x is equal to 0. Yeah. at x is equal to 0, you can actually write theta 0 is equal to t0 minus t infinity, and theta L is equal to TL minus T infinity. Okay. So based on that, you can actually have your constants. I'm not going into very much detail. It is a simple algebra only. We have actually seen it many times how to find the constants. Okay, so based on that, you can actually find what is actually C1 and you can actually find what is actually C2. Okay, so you can actually put it over there and you can actually get in terms of sine or yeah, you can actually get it in terms of sine. Okay, here again, maybe you can actually start with the hyperbolic function also. Okay, so you don't have to start with this. Okay, so you can actually start with hyperbolic function also. Okay. We can actually compare it with our constant temperature condition over here. Okay, so we have actually seen constant temperature condition during our lectures. Uh, I think somewhere over here. Can anyone compare the constant temperature condition with this? How different it is? Prescribed temperature condition. Okay. Yeah. Okay. So this is almost the same condition, right? So here you can actually see that